Okay, let's unpack this. Think about the roof right over your head. Most of the time, you just want it to do one thing. Keep the water out, period. End of story.
Right. That's the traditional view, certainly. Buildings are typically engineered to shed water, get it away as fast as possible.
Right.
But that rapid runoff, especially in cities with lots of concrete and asphalt, well, it can cause bigger problems downstream.
Like overwhelming the drains.
Exactly. Overwhelming drainage systems contributing to flooding and stopping water from soaking into the ground naturally.
And that's where our material for this deep dive gets really interesting. We've got a stack of sources here, articles, some research notes, all zeroing in on a different way buildings can handle water. Green roofs.
Yeah, so our mission today is to really dig into what these sources tell us about them. We're looking at their structure, their purpose, the different kinds, and maybe most importantly, the impacts, the benefits you can actually measure.
What's really important about putting, well, living systems on top of buildings.
Precisely.
So let's start there. Based on the sources, what exactly is a green roof system? It's got to be more than just, dumping some dirt and plants up there.
Oh, much more. The sources are pretty clear. These are highly engineered systems, multi-layered. They use natural stuff like plants, but also specialized synthetic materials working together.
Okay, engineered. And their main purpose isn't necessarily to keep all the water out. Which, for a roof, that sounds a little backward at first.
It does sound counterintuitive, yeah. But that's actually key to how they work. The goal, according to what we've read, is to actively manage the water. They're designed to significantly slow down and reduce the peak discharge, when it rains really hard.
So instead of water just sheeting off instantly.
Right. The system is meant to absorb it, hold on to it for a bit, and then release it slowly. This gives more time for water to soak into the ground around the building site. It mimics natural processes better than, say, a standard asphalt roof.
Spreading out the flow. Okay, that makes sense for managing stormwater. And you said layers. Those are fundamental to making this work.
Absolutely critical. If you look at the diagrams in the sources right at the bottom on the actual roof deck, you have an impermeable layer. Now, obviously, that keeps water out of the building itself.
Standard roof function there.
Yes, but it also does something else crucial. It acts as a root barrier.
Ah, right. So the plant roots don't start, drilling into the building structure.
Exactly, like tiny green drills, yeah. You definitely don't want that.
Good point.
Then above that barrier, you've got layers of synthetic materials. These act as filters and drainage pathways. They make sure water moves through the system correctly.
Got it.
And then on top, you finally have the growing media. That's the engineered soil and the plants themselves. These top layers are where a lot of the magic happens. Water retention, filtration, and even other things like co-euro absorption.
Okay, so it's a whole design system. Multiple layers, each doing a job, aimed at managing water differently. Who's pushing this idea then? Why is it on the radar of bigger organizations?
Well, this is where the General Services Administration, the GSA, comes into play, according to the sources. The GSA gives guidance and sets standards for how federal agencies manage their buildings. Think Department of Transportation, EPA, Department of Defense.
So they're kind of government's landlord, setting the rules for federal buildings.
In a way, yes. And the sources highlight that the GSA has been a pretty significant proponent of green roofs. They've been actively promoting them as part of their sustainable building initiatives for, the last 10 to 15 years?
Okay, a decade or more. And they link this to broader environmental goals, I assume.
They do. The material connects the GSA's push for green roofs directly to efforts to address global warming potential. It's presented as one piece of that larger sustainability strategy for federal buildings.
Makes sense. But it sounds like not all green roofs are built the same way, though. What did the sources tell us about different types?
You're right, they certainly are monolithic. The GSA, based on these sources, actually categorizes them into 4 main types. You've got single-course extensive, multi-course extensive, semi-intensive, and intensive.
Okay, extensive, intensive. What are the main things that separate those categories?
Several key factors. One is simply the thickness or depth of the growing media layer. Thicker layers generally allow for more design flexibility, different kinds of plants.
Right.
The drainage system also varies. The more intensive types might have a separate, distinct drainage layer, whereas the extensive types might integrate drainage functions into other layers, making them a bit simpler, maybe shallower.
And that thickness would directly impact the kind of plants you could actually put on them.
Absolutely. Thinner, extensive systems usually use lighter, coarser soil mixes that drain quickly. They typically support hardy, drought-tolerant plants, like sedums are really common, things that don't need deep roots or constant water.
Okay. Low maintenance, sort of.
Generally, yes. Thicker, intensive systems can hold more water and support a much wider variety of plants. You might even see shrubs or small trees on some intensive roofs, but they need deeper soil, obviously.
And probably more watering.
That's another difference, yeah. Irrigation needs. Extensive roofs often need little to no irrigation once they're established. Intensive ones, especially with more demanding plants, might need consistent watering, much like a regular garden.
Which types are more common then, did the sources say?
They indicate that single-course extensive is apparently more common outside the U.S. Within the U.S., multi-course extensive seems to be the most prevalent type being installed. Intensive roofs are the least common, likely due to cost, weight, and maintenance.
And speaking of weight, a really crucial point the sources emphasize, especially if you're thinking about adding one to an existing building, is the structural capacity.
This is huge, maybe the single biggest constraint, particularly for retrofitting. Green roofs add significant weight. You've got the soil, the plants, and critically, the water they hold after it rains.
Water is heavy.
Very heavy. A building that wasn't originally designed to carry that extra load simply might not be able to support certain green roof systems, especially the deeper, intensive ones.
So new buildings designed with a green roof in mind are probably engineered differently from the start.
Often, yes. They account for that added dead load and live load from the beginning. Retrofitting is much trickier.
Okay, so we understand what they are, who cares about them, the different variations, the weight issue. Let's get to the payoff.
Yeah.
What are the benefits that the sources really highlight? Carbon dioxide absorption is one, right?
That's definitely presented as a key environmental benefit. The plants do what plants do, photosynthesis. They absorb co-euro from the atmosphere.
And the sources actually point to a specific study that tried to measure this.
Yes, they reference an undergraduate honors thesis study. It was from 2019, University of Arkansas, Oxener, under Dr. Ben Runkle, and it provided a direct comparison, which is useful.
How did they set up the comparison?
They measured co-eros flux, basically, the movement of co-ero in and out on the green roof of a building called Hillside Auditorium. And they compared those measurements to a traditional roof nearby on the Biomedical Engineering Lab building, same campus.
Okay, green versus traditional. What did they find?
The key finding highlighted in the sources was that the green roof consistently showed higher KEO effluent flux. Now, efflux usually means going out, but in this context, because they were measuring the net exchange at the surface, higher efflux indicated more KEOs being drawn down from the atmosphere by the plants, so higher absorption.
Ah, okay, so higher efflux meant more KEO uptake by the green roof system compared to the traditional one.
Exactly. The study used box and whisker plots to show the data visually. You could see the difference in average values and the spread across percentile ranges over time. It's presented as pretty tangible evidence of that KEO uptake.
Measurable co-euro uptake. Got it. The other major benefit you mentioned earlier was runoff reduction.
Right. And this ties back directly to their main design purpose we talked about. By slowing down rainfall, holding it in those soil and drainage layers, they significantly reduce the total volume and the speed, the velocity of water that actually leaves the roof during a storm.
And the sources show this can actually be quantified, like with numbers, using standard engineering methods.
Precisely. They talk about using the rational method. It's a common formula, often used for smaller areas like building roofs, to calculate peak runoff. A key part of that formula, QCIA, is the C, the runoff coefficient.
Which is basically just a number that represents how much of the rain turns into runoff for a specific type of surface, like is it absorbent or not.
That's it, exactly. A highly impervious surface, like asphalt or a typical roof, will have a high C value, close to 1, meaning almost all the rain runs off immediately. The sources provide some data on green roof C values from different places. New York City, some studies labeled Moran, Mobile, also the city of Fayetteville's standards.
Okay, and what do those C values look like for green roofs in that data?
Well, the data shows they typically range somewhere between 0.35 and 0.7. This range depends on things like how deep the growing media is. They mention depths like 3 inches up to 15 centimeters, which is about 6 inches, and also the slope of the roof, usually for slopes less than 15 degrees.
Okay, 0.35 to 0.7. That sounds lower than 1. How does it compare to, say, a standard roof? What's the C value for a traditional shingle roof in that Fayetteville data?
According to the sources, a typical shingle roof in Fayetteville is assigned a C-value of 0.95.
Wow, 0.95 versus 0.35 to zero point 0.7.
Wow.
That's a really big difference.
It's a dramatic contrast, yeah, highlighted by the data.
So a shingle roof lets almost everything run off, while a green roof, even at the higher end of that range, cuts that runoff potential down significantly.
That's the key takeaway presented. The sources point out two things from this C-value data. One, green roof C-values are significantly lower than typical impervious roofs. That's the main benefit for runoff. But two, and this is important for design, there is that notable range, 0.35 to 0.7.
Meaning they don't all perform exactly the same.
Right. It introduces some variability, maybe potential uncertainty that engineers need to account for. Different green roof systems or maybe different storm conditions will perform differently within that range.
Let's make this even more concrete. The sources provide an example calculation, right? Using the University of Arkansas Mechanical Engineering building. This calculation really shows the impact of that C-value difference in practice.
Absolutely. It's a good illustration. The scenario is, what if you replaced the traditional shingle roof on that building with its C0.95 with a green roof? For the example, they use a green roof with an average media depth of 3 inches, and they pick a C-value of 0.50, which falls within that range we saw based on the Moran data cited.
Okay, C0.95 for the old roof, C0.50 for the new green roof. The building's roof area is given as 2,576 square yards, which the sources convert to 0.532 acres. That's the A in QCIA.
Right, and the rainfall intensity, the I, used for the calculation is 1.8 inches per hour, a specific storm intensity.
Got it. So using the rational method, QCIA.
We calculate the peak discharge rate, Q, for both scenarios. First, the original shingle roof. Q equals 0.95 times 1.8 inches shower times 0.532 acres.
Which works out, according to the source, to 0.906 cubic feet per second. That's the peak flow rate off the shingle roof.
Correct. Now for the green roof scenario, Q 0.50 times 1.8 inches shower times 0.532 acres.
And that comes out to 0.479 cubic feet per second.
So the difference in the peak discharge rate, you just subtract the two. 0.906 minus 0.479.
It's a decrease of 0.429 cubic feet per second.
Yeah.
So just by changing the surface of that specific roof, the peak rate at which water gushes off it during that particular storm event is almost cut in half.
It's a substantial reduction, yeah, almost 50%. That's the practical impact presented in the sources. And that decrease in the peak rate means the storm drains, the pipes, the streams downstream receive that water slower. It's spread out over a longer time.
Which reduces the immediate load on the system.
Exactly. Reduces stress, lowers flood risk, and promotes that more natural ground infiltration we talked about earlier.
That example really does bring the runoff benefit to life. Much clearer than just the C-values alone.
It shows the practical difference these systems can potentially make to local hydrology, one building at a time.
Okay, this has been a really good deep dive into the source material we had. We've seen that green roofs aren't just simple garden patches up high. They're complex, layered, engineered systems.
Right, designed with a specific purpose to manage water very differently than traditional roofs typically do.
We looked at how big players like the GSA are promoting them as part of sustainable building practices for government buildings.
And the sources detailed those different types, extensive, intensive, based on things like thickness and drainage. And we hit that crucial point about structural capacity, the weight.
Yeah, can the building actually hold it up?
A critical question.
And then we saw the tangible benefits laid out in the material, that measurable co-euro absorption highlighted by the University of Arkansas study. And the really significant runoff reduction powerfully shown by that calculation, almost having the peak discharge just by switching the roof type in that example.
They really offer a very different way for a building to interact with the environment it sits in, managing water, contributing to air quality potentially.
Exactly.
Yeah.
Tools for better stormwater management, maybe improving air quality in built-up areas.
That's how they're presented.
Okay, so we've seen these clear benefits. That measurable impact, like the runoff reduction example, is pretty compelling. But thinking about those structural limitations, we discussed the sheer weight issue, especially for existing buildings, and also that variability in performance suggested by the range of runoff coefficients, that 0.35 to 0.7. What does this material really tell us about the real-world challenges, the sort of potential speed bumps for making green roofs a truly widespread solution in our cities and on our buildings today?
That variability and the structural constraints are definitely key factors to consider for scalability.
Something for you to think about as you look up at the roofs around you next time it rains?